G'day guys, Mr. Bennett here. Today I'm going to talk about X-rays. So this is the first video on X-rays. You'll find this diagram of our X-ray tube in your book. Now, it sort of lists the parts of the X-ray tube, so we will not necessarily read the bits there, but I'm just going to highlight some things. So, in around this shape here, we have a vacuum tube. Right? The vacuum tube allows this to happen all under a vacuum, so therefore reduce the energy losses over there. We have a solid copper anode over here, which is a positive. So if we're thinking about this particular diagram, this is a positive and that's acting as a negative. So we have a filament there, a cathode terminal, and so therefore what's going to happen is you're going to produce electrons, and then they're going to get accelerated across this gap here, directed at the target, and you're going to have high voltages here, so anywhere up to 100 kilovolts. Okay, so quite high voltages there. What's going to happen is 99% of the energy is going to be produced as heat. So we have these cooling fins over here, which cool the X-ray tube down. 1% of those particular electrons is going to produce what we call over here as X-rays. Alright, so we'll actually do that. We want to go through the process of how that actually happens. So looking at this little nice diagram, so you can see essentially what we've got here is a way of producing electrons. Electrons that accelerate across here at a high voltage. They hit the target, which is generally tungsten. The reason why we use tungsten is because tungsten doesn't melt at low temperatures. Okay, so the X-ray gets quite hot, and so every time the electron goes in there, it can produce, well, actually not often, but it can produce these photons, what we call X-rays. Right, so they're just bundles of energy, just different forms of energy, I suppose. Typical sort of spectrums that you're going to see is this Bremsstrahlung shape. So you're going to have a maximum frequency over here related to that, and you see the intensity of the X-rays that are being produced. Alright, and I'm going to talk about that in a second. Obviously, if you increase the voltage, you increase the intensity and you increase the maximum frequency that these things are producing over there. Now, going back to just some formula stuff, we know that the work done is equal to Q delta V, which is the potential difference that you're accelerating the electrons across. We know that work's also equal to kinetic energy, which is equal to 1/2 mv squared. So therefore the velocity is really going to be equal to Q delta V, which is the kinetic energy, all over 1/2 of m, and you have to take the square root of that. Or you could write that as the square root of 2Q delta V all over m. So talking about electrons, so the charge of electron, the mass of electron, and the potential difference will work out the velocity of the accelerated electron over there. Now, what happens in the target metal? Because it's a metal, it's got delocalized electrons. Okay, so we'd want to talk about the spectrum itself first of all. So let's say in here we have a couple of nuclei. Alright, so we've got a nuclei there, and we have a nuclei down here somewhere. Alright, so what we have is we have a electron that's going to be accelerated across here, and it's going to split between the two of those. That's the path of my electron. That's not going to produce any X-rays. Alright, so the electron's not going to slow down at all, it's just going to go straight through there. What's going to happen here though, if it gets closer to that thing, it's going to bend slightly. It's going to slow down, it's going to be attracted to the nucleus. So as it's attracted to the nucleus, what actually happens, it will eject a photon with a certain amount of energy. Right, so as it slows down, conservation of energy says that some of that energy is going to be produced. Now that might be voltage number 1, right? So in terms of not the voltage, but in terms of getting closer to the nucleus. As it gets closer to the nucleus, what's going to happen is that electron is going to slow down a bit more. And so therefore what's going to produce will be a photon, which is basically got much greater energy. Call that energy, I suppose. Alright? And then as this thing gets closer again, what's going to happen is the electron is going to slow down even more. And so therefore you produce an even more energetic photon. Okay, and which has got energy number 3, energy number 2, energy number 1. And then the case that basically means that the electron's going to lose all of its energy is if it actually hits the photon, I mean the nucleus. And if that's the case, then what's going to happen is it's going to lose all of its energy, and that's going to produce the maximum X-ray that it can possibly do, and we're going to call that E4. So in terms of the energy, we know that energy for photons is going to be greater, or X-ray is going to be greater than energy of 3, and greater than energy of 2, and greater than energy number 1. Alright, so the maximum energy that it can actually have, and we know that energy is directly proportional to there, so we know that energy is directly proportional to the frequency. So if we increase the frequency, we increase the energy. So the maximum frequency of an X-ray that can be produced is when it actually hits the nucleus. As the electron gets closer to the nucleus, it's going to lose as it gets further away from the nucleus, it's going to lose less energy. It's going to slow down more, less, so therefore it's going to lose less energy. So the further it is away from the nucleus, the smaller the X-rays being produced, the energy of the X-rays being produced, and the closer it gets to the nucleus, the greater the energy X-ray is going to be produced. Maximum being when it actually hits the nucleus. Alright, so when we relate it to this particular graph here now, we've got maximum frequency, that's where it hits the nucleus. Right. And then the reason why it's a continuous spectrum is it can be at any distance from that nucleus. So as it is at any distance from the nucleus, it's going to produce a different energy X-ray, and so therefore that energy relates to the frequency. So we're going to get a continuous frequency range of X-rays that are being produced. All right? The voltage just changes obviously the maximum frequency that you would produce, because obviously the X-ray or the electron will be moving faster, so therefore it can lose more energy, can't it? Hopefully that makes sense. Now you might notice on these particular things over here is we see some spikes. Right? We see some spikes at particular energies. Right? And if you look down there, they sort of hit one space and then they hit this sort of space here. How do the X-rays produce those little spikes? Well, what also happens around around the nucleus, there are also other electrons orbiting around here. Right? So electron shells orbit obviously the nucleus, even though they are delocalized. So what can happen here as the as the electron comes through here, what it might do is it might hit, say, this electron. So we've got our electron coming in. It's going to hit that one, so it's going to knock it out. Right? And then what's going to happen is one of the electrons that are in a higher energy shell will in fact fall down from there down to there. And as it does that, it's going to eject a photon with a certain amount of energy. Right? And that energy is going to relate to the difference between the electron shells. So therefore, you're going to see quite specific spikes related to those particular frequencies which relate to the energies. Now, if we start thinking about that, the likelihood of it hitting an electron is going to be quite slim. So therefore, you're not going to see, a huge range of those sort of spikes there. But anyway, you might be asked to talk about why those spikes are produced, and that's what actually happens. All right. So hopefully this has been useful in terms of understanding how this all works.